Today we're going to talk about equations, specifically x and y intercepts and symmetry for equations. An x-intercept occurs where y is 0. So it's some value on the x-axis, but not up and down at all. That's an x-intercept. A y-intercept occurs where x is 0 because we didn't go left or right at all. It's somewhere on the y-axis. Okay, so our first equation, x squared plus y squared equals 9. You may or may not recall that's a basic graph of a circle with radius 3. So if you knew that, you could draw the graph and immediately identify the x-intercepts and the y-intercepts. If you didn't know that, you could find the x-intercepts by plugging 0 in for y and finding out that the x-intercepts are positive and negative 3. And you could find the y-intercepts by plugging 0 in for x and find that the y-intercepts are also positive and negative 3. Here's a basic graph of x cubed shifted to the right one. So it looks like this. Okay. So I could identify the x and y intercepts from the graph, but if you can't draw it, we're going to find the x-intercepts by plugging 0 in for y. Cube both sides. Add 1 to both sides, and we would get an x-intercept of 1, 0. To find the y-intercept, we plug in 0 for x. So we need the cube root of negative 1, and the cube root of negative 1 is negative 1. So the y-intercept is 0, negative 1. Our bigger topic is symmetry. Symmetry, and we're going to talk about 3 types of symmetry. Symmetry with respect to the y-axis, symmetry with respect to the x-axis, and symmetry with respect to the origin. Okay. This equation would make the basic graph of a parabola with a vertical shift of 2 units. We can see that the y-axis creates a fold line, if you will. The graph is symmetric with respect to WRT, the y-axis. And later on in the unit, we will say that that means that the function is even. It's just a preliminary bit of information. What you will notice about graphs that have symmetry with respect to the y-axis, any point that you take on the graph, there is a companion point across the y-axis, which would be the opposite of the x value with the same y value. The reason I mention that is because if you didn't draw the graph and visually check for symmetry with respect to the y-axis, you could do it algebraically by plugging in the opposite of x for x into the original function and showing that when you do that simplification, it is exactly the same as the original function or equation. Okay, here we have again a circle, only this circle has center at 4, 0, radius 2. It does not have symmetry with respect to the y-axis, but it does have symmetry with respect to the x-axis. There is no function equivalent for an equation that has symmetry with respect to the x-axis because it's not a function. If we look at a point xy then there will always be a point that is x opposite of y that is also on the same graph. So to prove algebraically that the x-axis is a line of symmetry, we would keep x, but substitute the opposite of y, and show that if we do that simplification, we end up with the original equation. Our third type of symmetry is symmetry with respect to the origin. Now that's not a line of symmetry, that is a rotational symmetry. So what I'm going to do, I've got y equals sine of x. I've drawn one way of going forward and one way of going backward just to show this symmetry. Symmetry with respect to the origin says if I took my graph and rotated it, and I'm just a little offline here, and rotated it, it would look the same right side up and upside down. That's symmetry with respect to the origin. And visually, we say if it's a function, we say it is an odd function when it has symmetry with respect to the origin. If I pick a point, let's call this point x, y. Symmetry with respect to the origin says there's a point over here that would be the opposite of x and the opposite of y that is also on that equation. So for this, I would substitute negative y for y and negative x for x and show that I can come back to the original. Well, this is going to, since this is trig, it's going to require an identity. The sign of negative x by the even and odd identities says that that is the negative sign of x. And if I multiply both sides by negative 1 or divide both sides by negative 1, either way, I come back to y equals sine of x, my original equation. Okay. If you already know your basic graphs, you can stop watching this video. If you don't, stick around for a moment to see our basic graphs. These are graphs I expect you to know. Our first one, y equals x, we should all know, is a line coming through the origin with slope 1. Y equals x squared, we should recognize as a parabola with vertex at the origin. Y equals x cubed is a cubic graph centered at the origin. Right, if I plug in 1, I get 1. If I plug in 2, I get 8. If I plug in negative 1, I get negative 1. If I plug in negative 2, I get negative 8, like that. Y equals absolute value of x, which in the first quadrant looks like y equals x, but in the second quadrant, it actually happens that negative 1 is 1, and negative 2 is 2, and negative 3 is 3. So it actually sort of bounces off the origin. Y equals the square root of x. Well, we're not taking the square roots of negative things. Those are imaginary. So the first thing I could take the square root of is 0. And then the square root of 1 is 1, and the square root of 2 is ugly, and the square root of 3 is ugly, and the square root of 4 is 2. The next one that's nice is the square root of 9. So it does sort of a slow rise out this way. Y equals the cube root of x. Well, I can take the cube root of a negative thing. Cube root of 1 is 1. Cube root of 2 is ugly. Cube root of 3, 4, 5, 6, 7. Cube root of 8 is 2, so it's doing an even slower rise out this way. Cube root of negative 1 is negative 1, and the cube root of negative 8 is negative 2, so it looks kind of like that. Those are our basic graphs.